right, so today we actually get to multiply vectors together. We also get to talk about work, those of you who have had physics before. Okay. All right, so the dot product is our way of multiplying, okay? So if we have vector u and vector v, notice how I've labeled their component as like component 1, component 2, okay? This is how we find the dot product. So u dot v. It just looks like a multiplication sign, but when we are in vectors, we call it the dot product. U dot v. Go ahead and write it down and we'll talk about it. So to find the dot product, we are going to take the horizontal components and multiply them together. We take the vertical components and multiply them together, and then we add those two numbers. It is important to realize that the dot product gives us a scalar, not a vector. Okay. When we take the dot product, we just get a number. Okay, so here are the two vectors that I'd like to find the dot product of. V is the vector, negative 2i plus 5j. W is the vector, 4i plus j. So to find the dot product, we will multiply negative 2 times 4, because those are the horizontal components, plus 5 times 1. Those are the vertical components. Did I say that backwards? Okay. Negative 2 and 4 are the horizontal components. 5 and 1 are the vertical components. So our dot product is negative 8 plus 5, or negative 3. And that's it. That's all we have to do. You try. You find me the dot product of u and v if we have 2, 1 and negative 1, 0. Lori, talk me through how you did this problem.
did 2 times -1 plus 1 times 0. And I got -2.
All right. Give me a thumbs up if you agree with Morgan. -2. Awesome. Makes it nice when there's a 0 as one of the components, doesn't it? Okay. All right, we're going to look at some properties. Okay, remember when I taught you vector addition, we looked at some properties like the associative property and commutative property. What holds true for vector addition? Okay, well, what holds true for vector multiplication, or in other words, the dot product? Okay, you don't have to write these down; these are in your book to reference. Okay. First property, the dot product is commutative. It doesn't matter which order they're in because you're still multiplying the components together, and that kind of multiplication is also commutative. Okay. Dot product with 0 is going to get you 0. Okay. That should be pretty obvious. Number 3. So this is kind of like our distributive property. Okay, if we're taking the dot product with a sum, that would be the same thing as taking u dot v and adding it to u dot w. Okay, our dot product is like multiplication, so we can distribute that through. Okay, here's a very interesting one. The dot product of a vector in itself is the same thing as the magnitude squared. Okay, let's talk about why that is. Let's say our vector is AB. Then if we take v dot v, then we're going to take a times a and add it to b times b. Well, isn't that just a squared plus b squared? Right? Which is underneath the radical of our magnitude. Okay? So dot product of a vector with itself gives you the square of the magnitude. Okay? Not something I don't think we're going to use a whole lot in here, but interesting thing to think about. Okay? All right, this is important. Okay? C is a scalar multiplied to a dot product. Okay? If we think about regular multiplication, 2 times 3 times 4, okay, we don't take 2 times 3 and 2 times 4, do we? No. We take 2 times 3 and multiply it to 4, or we take 3 times 4 and multiply it to 2. Okay? Same kind of thing here. If you have a scalar multiplied to a dot product, these are all seen as multiplication. So you can either multiply the scalar to u and then take the dot product, or take the scalar to v and then take the dot product. You'll be asked to do some operations with dot products. Just make sure you keep things in order as far as moving left to right, doing things in parentheses. You're going to do some problems which you'll have to like mix addition and multiplication together. Okay? But what's the point of the dot product? Okay, the dot product, it gives us a number, woohoo, right? What can we do with that number? Okay? The first thing that we can do with the dot product is find the angle between two non-zero vectors. Okay? So go ahead and write this formula down right here. This is going to help us find the angle between vectors. Okay, so let's say you have two vectors, all right? So, yes, it's possible for me to find the direction of vector u, and then find the direction of vector v, and then figure out what the angle is in between. Or, if we know the components of each vectors, we can use the dot product and their magnitudes to find the angle that's in between. Okay. Now, there's a couple of things that we need to realize about using this. Okay. The inverse cosine is only going to give you angles between 0 and what? 180. Okay. Remember, inverse cosine gets us angles in the first and second quadrant. Okay. So when you use this formula, it's always going to find the shortest angle between two vectors. Okay. If I draw two vectors up here, okay, technically, you could argue that there's two different angles in between the vectors. Okay. There's this angle here, or there's this angle here. Okay. That formula is going to find you the shortest one. Okay. If you get that angle to be 0 or 180, I need to add that in, then the vectors are going to be parallel. Okay? 0 means those vectors are going in the same direction. 180 means they're going in opposite directions. So we're going to take those two vectors that we had in our first example, negative 2i plus 5j and 4i plus j, and we're going to find the angle in between those. Okay? Now, can someone remind me what the dot product was? Yes. And we found it for these two vectors, didn't we, already? Yeah. So it's negative 3. Okay. Now we're going to need the magnitude for each. So pods 1, 2, and 3, please find me the magnitude of V. Pod 5 and 4, 5, 6, find me the magnitude of W. I would leave it in radical form. It'll make it easier. All right, Michaela, so what did you get for the magnitude of V? Pods 1, 2, and 3, do you agree? Awesome. Michael, what did you get for magnitude of W?
Radical 17.
Pods 4, 5, and 6, do you agree with that? Awesome. Okay, I would leave them as radicals. All right, it's going to be easier to use the formula. So the cosine of the angle in between our vectors is the dot product over the product of their magnitudes. Okay, so in your calculator, you are going to have to use what? The inverse cosine. Okay. If you're going to put this in all at once, notice how you have two different numbers in your denominator. You need parentheses around them because you have to divide by both numbers. Okay? Okay, Sean, what'd your calculator give you?
I got 97.34.
And 97.77? Did you do some rounding before you took the inverse cosine?
No.
Here's your calculator. It's because the square root is 17.
Oh.
You have 19. Okay. If you're worried that you might forget about those parentheses, okay, we can multiply radicals together. And so this is the same thing as the cosine of theta, -3 over the square root of, what is 29 times 17?
493.
If you would rather do that, that is a possibility. Okay. All right. So the angle in between our vectors is 97.77. Okay. Let's go ahead and plot these vectors and make sure that makes sense. All right. So vector V is -2, 5. And vector W is, yep. It's Friday. Gloomy weather on Friday. Is there a good day? Okay. All right, and then 4, 1. Does that seem like a reasonable angle to be between? It looks pretty close to a 90-degree angle, 97.77. That seems reasonable. Okay. Now, let's think. Okay. First of all, new word, orthogonal. Okay. I want you to break down the word orthogonal, what you guys know about the English language. What do you think it could mean if two vectors are orthogonal? Okay, turn to your neighbor and make a guess. Orthogonal. What does it mean for two vectors to be orthogonal?
This orthodontist makes your teeth straight.
Orthodontist makes your teeth straight. Okay, I hear a lot of orthodontists talking, right? Okay. So, Michaela, you guys are talking about orthodontists. What do you think about two vectors being orthogonal? Straight? Anybody have it? You guys kind of talk the same thing, straight.
They mean parallel.
Okay.
They're straight.
Any other ideas? It actually means perpendicular. Okay. Well, let's think about your teeth being straight. Don't they need to be like perpendicular to your gums? You know what I mean? The word ortho, or not the word, but prefix ortho, means, it could mean straight, it could mean upright, it could mean right, it could mean correct. So upright, right, okay, that's kind of where it's coming from. Okay, so you guys were on the right track. I'm glad you thought of the orthodontist. Okay, now what we need to think of, how could I use the dot products to figure out if we have orthogonal vectors? So I'll write this up here. Okay, I want you to turn to your pot and I want you to think about, okay, first of all, what would theta need to be for orthogonal vectors? 90. Okay, so if our angle is 90, how are we going to know without even having to use that formula? or what would the right side of the formula need to be if that angle is going to be 90 degrees? Turn to your neighbor for a few seconds and talk about that. You guys are awesome. Okay, pod 4. What's the cosine of 90? 0. So what does that mean about the right side of our equation?
True.
Okay, which part of that fraction needs to be 0? Okay, we don't want the denominator to be 0. If the dot product is 0, automatically we have orthogonal vectors. We don't even have to use that formula because we know that the cosine of 90 degrees is 0. Okay? So if you take the dot product is 0, automatically. These are orthogonal vectors.
Yeah, sir.
Has anything in vectors been a form of word?
Vectors.
Magnitude instead of length. Right?
Well, 92 isn't necessarily like true.
Well, okay, so we are going to determine if these two vectors are orthogonal. All right? If I'm asking you if they're orthogonal, the first thing we need to do is find their dot product. To find their dot product, we're going to take 2 times, everybody? 6 plus negative 3 times
4.
And what is that?
0.
0. So these are orthogonal vectors. Now, if the dot product was not 0, you would want to go ahead and find the angle in between using that formula. If the angle is 0 degrees, what does it mean? Parallel. If it's 180 degrees, parallel again. Okay, perfect. Are you ready for some physics? Somebody from physics, how do you find work?
Ask Mr. Marshall.
Force times displacement.
Very good. Force times displacement.
Good job, Tyler.
However, the force that we use for this formula has to be in the direction of the motion. Okay? If I take Kyler's chair and I start pulling him, okay, which way is he moving?
The way you're moving.
Okay, so is he moving at an angle? I'm pulling at an angle though. He's moving horizontally, isn't he? So the only force that matters is the horizontal force. Okay? Because that's the direction that he was moving. Okay? Even though I'm pulling or pushing at an angle, he's moving horizontally, so the only force that matters is the horizontal force. Okay? Yes. Components. Yes. So, you know, yesterday when we found our different components, there was a reason for that. Okay? So, we are going to do an example with a tractor pulling a log. Okay. Are you kidding me? A tractor pulling a log? This is about like as real as it gets. Okay? Okay, so we have a tractor pulling a log.
Wow.
The picture doesn't really matter, okay? This is our tractor, and it's pulling a log, 800 meters, and it's the steering wheel. The tension of the cable is 1,600 kilograms, okay? So, here's the log. And it's, so here's the green graph.
So the tractor's floating.
There's the grass. Okay, so this is making a 35-degree angle, and the tension is 1,600 kilograms.
Sweet.
Okay, 1,600 kilograms, that is the force. Now, if that log is moving horizontally, what is the force that matters?
The horizontal force.
The horizontal component is the only one that's really acting on this log. Okay, so our force is the horizontal component. So 1,600 kilograms times the cosine of the angle. Okay. What's our displacement?
800 meters.
800 meters. So our work is force times displacement. Multiply those two together. What is that big number?
Wow. 104,840.
Something like that? It's a lot of work. Now, let's talk about our labels, okay? Not everything is joules. It's only joules if it's Newton times meters, correct? Okay, so what did we do? We took a force of kilograms and multiplied it by a displacement of meters. So our label is kilograms times meters. I know it's strange, but that's what it is. You'll also see like some foot pounds. Feet times pounds. Okay? Just whatever your labels are, you have to multiply those together as well. Okay? The biggest thing here is that the force has to be the component in the direction that it's moving. Most of your examples are going to be horizontal. Alright? So this is your homework. Alright? Make sure you do those work problems because there will be a work problem on your quiz on Tuesday. On Monday, we will take some time and we will review all of our vector components. No? Okay, thanks. So we'll take Monday and we'll review all of our vectors. You might be a little rusty coming off the weekend on the things we learned maybe way back Wednesday. And then Tuesday we'll take a quiz and you'll have a problem set after the quiz. Okay. There is one more section after our quiz. So we'll spend like Wednesday, Thursday on section 5. We'll spend Friday, Monday reviewing, and our test will be the Tuesday before spring break, and then we'll finish out the week with the project. Out of curiosity, how many of you will be gone for sure the Friday before spring break? The Thursday before spring break? The Wednesday before spring break? Excellent. So Thursday, Friday. Oh, state DECA. And then isn't there like a fire show?
Oh, yeah. I think like the last, maybe Friday, maybe Thursday. I know Friday, but maybe Thursday.
Okay.
I completely forgot. We're going to.
Well, and aren't you skiing too?